Welcome, everyone, and thank you for attending today. My name is Mark Steen, and I'm the General Manager of Midland Technologies based in the Minneapolis-St. Paul metro area. We are pleased to present this series of webinars Midland has developed focused on the high-pressure die casting industry. Midland, along with its sister companies, are a part of a 100% employee-owned organization. As owners, we are dedicated to providing our customers with the highest quality products and customer service. Today, I have Larry Winkler, who is the president and owner of AWIN Tech Diecast Consulting. In 1996, Larry developed and implemented vacuum assistance and chill blocks in the die casting, and a year later, working with Midland Technologies, commercialized the product. Larry has over 35 years in the die casting industry at 5 die casting companies in a variety of engineering roles. In addition, I have Bill Zabracki, who is our product engineer here at Midland, where he designs and coordinates all engineering activities. Bill has 30 years in the manufacturing industry, ranging from electromechanical circuit board test units, hydrostatic high-pressure valves and pump systems, and now high-pressure die casting components, with an emphasis in designing, managing operations, and quality control. If anyone has questions, please submit your questions via the chat feature. Thank you again, and I will now hand it over to Larry and Bill.
Thank you, everyone. This is Bill Zabracki. I appreciate everybody attending our webinar this morning. We'll be talking about increasing profits through the reduction of metal loss. And today's topics will be covering potential savings related to metal loss. Where is metal loss in die casting, in the die casting process? Metal loss from flash, as we all know, and the cost related to flash, and also reclaiming flash. And we'll be also covering cause of problems with remelting flash, method of reducing flash. And we'll actually go through an actual experience with a die caster. And we'll be talking about the different methods of evacuation and also savings calculations. So we got a lot on our topics today. And again, like Mark indicated, if you have any questions, please submit them in the question box or the chat box, and we'll answer those questions at the end of the presentation. And so the first one we're going to talk about is potential savings related to metal loss. And of course, the advantage of the die casting process is the capability to recycle material. And I think we're all aware that it's something that each die caster is trying to do. And that recycled material can come from runners, overflows, gates, and scrap that can be remelted. Material loss then can occur when flash is created. And where is the metal loss in the die casting process? So with the flash, if the overheating metal in breakdown or the holding furnaces, and the improper metal handling and melting, and all this will produce a scrap casting. And producing scrap casting too is where metal loss can occur. And you can only reclaim a percentage of the metal. You also can have loss with biscuits, runners, gates, and overflows. And you can only reclaim a percentage of that metal as well. And of course, flash. And unfortunately, with flash, it cannot be reclaimed. So I'll pass on now the presentation over to Larry.
Good morning, everyone. I think all the die casters in the group, and there should be, hopefully you're all die casters, are aware of the loss of metal from flash. This is probably an extreme example with the photo we have here, with the die not being either properly fitted, or the die casters backed off the locking pressure of the machine.
One second here. There we go.
Okay. So as you're all aware, insufficient locking force can be contributed to this amount of flash. Poor shutoff design or tools construction can also be part of that. In addition, the part features and the method of cavity evacuation. So cost related to flash. This photo just shows a typical collection of flash in a plant, and that initial cost of the material, what we're looking at is the material compared to the amount of flash generated. So each and every die casting, of course, has a potential to generate flash. Collecting the flash, of course, can be an issue too. Just collecting it in your plant, associated with cost, the cost of the storage space to maintain the flash. Containers, of course, you have to have containers to collect the flash. The cost to dispose of it. Some of the flash, if it's clean, if you talk to your smelter about it, you'll find out that they'll take the flash back sometimes. Other times you have to dispose of the flash, and of course, in those instances, if you go to a landfill with flash, that's a cost normally to the die caster. And then, of course, you've got the cost of shipping the flash. Reclaiming flash. Flash remelted is not reclaimable. The majority of that is just going to turn into, if you try to remelt it in your plant, and if you've done this, you know that it creates oxides. And those oxides not only affect the alloy itself, but they'll also decrease the efficiency of your remelt furnace. So cause of reclaiming issues with flash. Thin flash, that thickness is less than 25 thousandths, are non-reclaimable pretty much. Even we've talked to smelters. Obviously, our vents, normally the atmosphere, are usually no thicker than 5 to 6 thousandths in a conventional vent. So all of that material is totally wasted. Methods of reducing flash would be installing a method or a series of runners using either a chill block or a valveless vacuum block. So either one, you can reclaim the majority of the flash as pictured here. The only portion you couldn't possibly, even though it's over 20 thousandths thick, the actually serrated portion of the vent or of vacuum block could not be remelted. So next we're going to talk about an actual experience that a die caster related to us. This die caster indicated he was losing flash off. He was losing money and metal related to flash that was totally unreclaimable. And so he he had very little success in getting the smelter to give him anything for his reclaimed flash. In this instance, he installed a valveless vacuum block and was able to reduce his metal loss.
Okay. And this is Bill Spracky again. I'll take it on from here. So the ways of reducing the metal loss would be we'll cover some of the evacuation methods. So everyone's well aware of the conventional vent, where the air is being pushed out of the cavity to atmosphere ahead of the metal or with the metal. And in these cases, the vent system must be large enough to allow the air to escape. And you can see the picture there of a small the small area of the metal going to atmosphere. Now the depth from the cavity or overflow to the edge of the insert is typically 20 inches, and then from the insert to the atmosphere, you just have a very small depth of 0.005 inches. So it's not a real big area that you can cover with a conventional vent. And then also you have to be concerned with, as the air travels through, air travels at the speed of sound when confined, and this may actually limit the ability of the air to evacuate. And of course, the flash is not reclaimable. And you also have a few things that could fail the function, either with a spray buildup or with flash sticking in the vent, and also when the vent gets peened over. So the other evacuation methods that we'll look at are with the vent blocks, and the first one is a vent block where the air is being pushed out of the cavity through atmosphere through a serrated block. So again, it's being pushed out like the conventional venting, but it's going through a serrated block, as you see in the upper right hand corner. Now the advantage of that is that the evacuation area to the atmosphere is much greater than a conventional venting. So you could have one vent block in place of a number of conventional vents, depending on the evacuation area that you need. The other method is with a valveless vacuum block, and with a vacuum block, the air is being pulled out of the cavity through the serrated block. And down in the lower right is an example of a valveless vacuum block with the you see a round nipple in there that the vacuum hose would be attached to. And the evacuation process is assisted by the creation of vacuum using a vacuum pump. And with the advantage here is that the smaller passages can be used and less time is needed to evacuate the cavity. So next we'll kind of look at savings calculations. And with the die caster that we had previously talked about, here they had a situation where the vent area required was 0.067 squared inches, and the total weight of the flash that they were getting was 0.146 pounds. Again, the vent dimensions 0.025 to 0.005, vent length average 3 inches by 1 1/8 inch, and basically the total vent width required was with 0.067 squared inches divided by 0.005. You needed 13.4 inches of venting, conventional venting for this application. They converted their to a vent block using a 4,000 size block, which has an evacuation area of 0.070 squared inches. And with the conventional vents, the metal loss, the cost was basically 0.146 pounds times your average of that point with for aluminum, $1.35 $1.35, and so they're losing 0.197 per shot. And as they converted over to using the 4,000 block, a serrated block, the loss of metal reduced to 0.019 pounds, and so they were only losing 0.026 per shot, and a savings of 0.17 per shot, 17 cents per shot. So with the savings calculations then for a whole year, the average shot per hour from machine utilized in this case 12 and a half hours per day. Average shots per hour 85, And if you take all that and figure out you have about just over 260,000 shots per year from one machine. So the potential yearly savings in unreclaimed metal would be 17 cents times the 260,000 plus shots. And so you're looking at a savings of 44,253 per machine. So quite a big savings. And if we look at the justification, you do have the cost of the block, which typically is about $39.14 for a vacuum block, and then also a little bit less for a non-vacuum serrated block. And with the metal savings per part of 0.17 each, you basically you get your payback after 23,000 shots. This savings does not include reduction in scrap with adequate cavity evacuation. But you get a good turnaround with your investment in a serrated block in a vent block or a valveless vacuum block. And those are the benefits that we see that people can incur when they switch from a conventional venting to a more of this style of evacuation. And with that ends the topics, and now we are open to any questions that you might have. Let's see if we have anything here. And let's see here. Okay. It doesn't appear we have any questions. Okay. Well, anything you can add at all, Larry? Or
no, just that I've experienced this myself in plants, and if just a real quick check you can make on jobs that you're suspecting may be candidates, number one candidates, because of probably running scrap. That's what motivated me in plants to go to to utilize blocks instead of using conventional vents. You can see how much potential savings you can realize by using either one of them. Not only that price, but as Bill mentioned, in reducing the scrap itself in your plant, you can realize quite a bit just by using a chill block. All of that, the runners and so forth, can all be reclaimed. The majority of it's all reclaimed when you remelt. Again, obviously, because of the thin vent, you can't reclaim it. So that's
and I think that the area that you have available for putting in the conventional vents, in some cases you need quite a few conventional vent tracks out to atmosphere. And when you switch over to a one chill block, you don't you may have less of a you need perhaps less area to put that block in, and it might not you might have an easier time as far as designing room for a block, or a chill block. So it's certainly something to consider when you are designing your output runners.
Right. And the other advantage is I've experienced is the fact that when you use these runners, you're tying everything together, material. I've had experiences and actually run in plants where we used overflows, and then usually in a lot of cases, die casters will attach a runner from overflow to overflow so that they're connecting them so that they can be easily handled as scrap. And one of the problems with overflows, if you don't do something to handle them, you've got the cost of trying to collect them at some point during your operation. Where using this method, where you've tied them together, with a good design of the outlet runner, either vacuum or vent. If you just tie them together in the conventional manner, you can actually feed metal and air back into the cavity, and I've seen that happen because the outlet area off of the casting to lower than the outlet to atmosphere. And subsequently, what will happen is metal and air can be driven into one and fed back into the cavity and create a bad casting and create and put air back in the cavity. So you're kind of defeating the purpose. It's real critical that the outlet locations for overflows be adequately spaced. A lot of die casters use overflows to heat the dies. I think that's less. Back in the day, I know a lot of times we would use them for heating a die or helping heat the die. But today, that's not necessarily with the advent of oil and different means of heating and tools while you're running. So the main reason you would use an outlet or an overflow or a jack off the casting would be to lift the casting, help to eject the part. So something to keep in mind when you are considering where you're going to locate those overflows, or hopefully will be the last place to fill. As Bill mentioned too, if you recall back in the earlier slide, it indicated that with a 5,000 gate to atmosphere, you needed 13.4 inches of vent, and a lot of castings, that's the entire periphery that would be required for venting adequately. There goes the old, I guess, the wives' tale that, well, if you back off the locking pressure of the die, you let the die breathe. Well, of course, you do that, but you also lose pressure on the metal, which is necessary to make a good casting in the interior. So there are a lot of advantages of going this way, opposed to doing things in taking a non-positive approach to and just trying to make a good casting is difficult enough. So I don't know if there's any questions yet. Apparently, we don't have any questions. So.
It doesn't appear that we have any. So,
well, we thank you for attending this webinar.
And if you do have any questions, you certainly can contact us at info@midlandtechnologies.com. And if you think of any questions later on, or if you have any other questions or interest in some other product that we may have, you certainly can contact us as well. Well, thank you again, everyone, for attending our webinar this morning. And we hope that everyone has a good rest of the day.
Thank you.
Thank you.